Welcome to the second half of the 8.5 lesson on factoring quadratic trinomials. Our objective: I can factor unique trinomials in the form some number x squared plus or minus bx plus or minus c. This video will specifically look at looking at very specific cases when a is not 1, but other characteristics will be met, as well as multiple variables. So let's look at some very ultra-specific cases of x squared plus or minus bx plus or minus c. And you'll notice right off the bat that a is not 1 in any of these cases. Both of these quadratic trinomials do have something in common, though, and it's that they have a greatest common factor. In the first one, 5x squared plus 40x plus 60, every term is divisible by 5. So if you divide out your a value, in this case 5, which is also your GCF, you're left over with a quadratic trinomial that's has an a value of 1, x squared plus 8x plus 12. So if we factor out a, and if a is a factor of every term, then we can go ahead and use the tricks that we already know and the patterns on how it works. So if you pretend this problem is almost just x squared plus 8x plus 12. What adds to 8 and multiplies to c, 12? Well, the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. So which combination of those add to 8? So 2 and 6. So x squared plus 8x plus 12 factors to x plus 2 times x plus 6, but we still have that 5 on the outside because it still needs to be multiplied by that. And so this is the fully simplified factored form. So 12y squared minus 72y plus 96 is your a value a factor of everything? Well, 12 does divide 72 and 96, so we can factor out the 12. We're left over with y squared minus 6y plus 8. And again, we're just going to pretend it's like its own separate problem. What adds to b, negative 6. What multiplies to c, positive 8. Factors of 8 are 1 and 8 and 2 and 4. So what combination of that can produce negative 6? Well, y minus 2 times y minus 4. When b is negative and c is positive, you know it's going to be a double y minus times y minus. So we have 12 times the quantity y minus 2 times the quantity y minus 4. And that will, when we redistribute the 12, we get 12y minus 24, and then we redistribute that 12y minus 24 into the y minus 4, and we get back to that 12y squared minus 72y plus 96. So this only works if a, b, and c are all divisible by a. Future lessons we'll talk about what to do when a is not a factor of b and c. You can also factor out multiple variables, but they have to follow a very specific pattern. So some trinomials have more than one variable. So let's consider, p plus 9q times the quantity p plus 7q. So if you were to distribute, p times p is p squared, p times 7q is 7pq, 9q times p is 9pq, and 9q times 7q is 63q squared. So you'll notice here a is 1. We have p squared. We have a middle term. The 7pq and the 9pq can be combined. They're like terms to give us 16pq. And then our last term is 63q squared. So a couple of things need to be true for this to be factorable. Number one, it is only factorable in certain cases. The first term must be the square of one variable. So, for example, p squared. I can't have anything else. The middle term has to have both variables in there. So if my first term is p squared and my last term is q squared, I have to have a pq in the middle. And it needs to have those like terms that add up, but that will make it factorable or not. And then the last term is the squares of the other variables. So if the first term had p squared, the last term must have q squared. All of our other factoring rules still apply. So let's look at an example, x squared plus 6xy minus 55y squared. I know it's going to be factorable, not because of the numbers, but because of the variable combinations. I got an x squared at the front and something y squared at the back, and I got an x to the first and a y to the first in the middle term. So assuming the numbers are factorable, it's going to be in the form x plus or minus something y times x plus or minus something y. So from here, we're just going to pretend the x's and the y's aren't there, and we're just going to look for a number that adds to 6, b, and multiplies to negative 55, r, c. So factors of 55 are 1 and 55, and 5 and 11. Not a lot of wiggle room here. It has to be x plus 11y times x minus 5y, because 11 plus negative 5 is 6, and 11 times negative 5 is negative 55. So having the template is a really good method to keep track of the variables. Otherwise, it's very easy to lose track. For the second one, again, we see right off the bat we are going to have the factored form because I have an m squared in the front and an n squared at the back and an mn in the middle. If, let's say, it was 6m squared n in the middle, then it would not be factorable using this trick. So I know it's going to be in the form of generally some m times some m plus or minus some amount n times m plus or minus some amount n. And so we just got to put in a sign and numerical coefficients for n's, and we'll be good to go. So we're looking for two numbers that add to 6 and multiply to negative 27. So the factors of 27 are 1 and 27, 3 and 9, and that's it. So what combination will give you positive 6? Well, that's going to be positive 9 and negative 3. So m plus 9n times m minus 3n. So it's almost using the template and then pretending the variables aren't there anymore, and then using the add to b multiply to c trick that we already knew from 8.5. Well, what happens if I merge these two things together? Well, I can factor very specific trinomials as long as they are the variable pattern is there, and there's a GCF. So 19a squared plus 171ab minus 418b squared. So right off the bat, can we factor 19 out of everything? Is a common factor of b and c? Yes, 19 can factor out, and we're left over with 19 times a squared plus 9ab minus 22b squared. From here, we're going to see, does the variable pattern work out? Yeah, I have an a squared in the front, something b squared at the back, and an ab in the middle. So I know it's going to be 19 times a plus or minus some amount b times a plus or minus some amount b. So what adds to 19 and multiplies to negative 22? Well, the factors of 22 are 1 and 22 and 2 and 11, and that's it. So how do I get 9 out of that? Well, I'm going to need 1 to be positive, 1 to be negative to get the negative c value of 22. And so b is positive, so I know my bigger factor needs to be positive, so it's going to be 11 and negative 2. So it's a plus 11b times a minus 2b, and don't forget the 19 at the front, which still is there as the GCF. If I were to distribute the 19 into the a plus 11b and then distribute whatever that sum is into the a minus 2b, I would get back to 19a squared plus 171ab minus 418b squared. So these are two ultra-specific cases. When a is a factor of b and c, and when the variables are in this very specific pattern.